Objective: to study the close packing of particles in 1 and 2 dimensions in solids. During the formation of crystals, constituent particles such as atoms, ions, or molecules come closer and become closely packed. When we say the arrangement of particles is closely packed, it means that the arrangement occupies the maximum space available. This corresponds to a state of maximum density. The closer the packing, the greater is the stability of the packed system. Such an arrangement of equidimensional objects in space, such that the available space is filled very effectively, is known as closed packing. As solids are three-dimensional objects, closed packing can be done in 3 ways. That is, closed packing in 1 dimension, closed packing in 2 dimensions, and closed packing in 3 dimensions. Before understanding each of these in detail, let us assume the constituent particles to be hard spheres of identical size. Let's first understand closed packing of particles in 1 dimension. There is only one way in which spheres can be arranged in a 1-dimensional closely packed structure. That is, in a single row, with the spheres touching each other. In this arrangement, each sphere is in contact with 2 of its neighbors. The number of nearest neighbors of a particle is defined as its coordination number. Therefore, the coordination number of a particle or sphere in 1-dimensional close packing is 2. Let us now look at close packing in 2 dimensions. A 2-dimensional crystal plane is generated when a number of rows of particles are stacked up. In 2-dimensional packing, there are 2 ways in which rows can be stacked. One way is for the rows to lie one above the other, with one sphere exactly above another. In this arrangement, the spheres are aligned horizontally as well as vertically. If the arrangement of the spheres in the first row is said to be of type A, then the arrangement of the spheres in the successive rows is also of type A. The packing thus obtained is called AAA type packing. Furthermore, each sphere is in contact with 4 other spheres, 2 on either sides, 1 above and 1 below. So the coordination number here is 4. By joining the centers of these 4 spheres, you will get a square, which is why this type of close packing is also referred to as square close packing. The alternate way of stacking the spheres in 2-dimensional packing is where spheres in every second row are seated in the depressions between the spheres of first row, and the spheres of the third layer are placed in the depressions of the second layer, and so on. Observe that the spheres in the third row are vertically aligned with the spheres in the first row. A similar pattern is noticed throughout the crystal structure. If the arrangement of spheres in the first layer is of type A and that of the second layer is type B, then the arrangement of spheres in the third layer is again of type A and that of fourth layer type B. The packing thus obtained is called AB-AB type packing. Observe that each sphere in this arrangement is in contact with 6 other spheres, 2 on either side, 2 in the layer below, and 2 more in the layer above. Therefore, the coordination number of the sphere becomes 6. Interestingly, we get a hexagonal pattern when the centers of these 6 spheres are joined. The reason why this type of closed packing is referred to as hexagonal close packing. Compared to square close packing, the atoms in hexagonal close packing are more efficiently occupied. Therefore, atoms or constituent particles usually follow hexagonal close packing in a plane, or 2 dimensions, to arrange themselves. In these arrangements, observe that some spaces are left vacant in between the close-packed spheres. These vacant spaces are called voids, or interstitial sites. These empty spaces can be observed as curved triangular spaces. When observed closely, we notice that these spaces are of 2 types. There are spaces in which the apex of the triangular spaces is pointing downwards. These are marked as B. And there are spaces in which the apex of the triangular spaces is pointing upwards. These spaces are marked as C. As real crystals are all 3-dimensional in nature, in the upcoming modules we will use 2-dimensional hexagonal close packing of particles to build 3-dimensional structures. Let's summarize. The coordination number in 1-dimension close packing of particles is 2. In 2-dimensional square close packing, the coordination number is 4. In 2-dimensional hexagonal close packing, the coordination number is 6.